Hello, my name is Thomas DeLuca.
My name is Julia Ludwiszewski. In this presentation, we will explain how chemical equilibrium thermodynamics relate to the Haber-Bosch process.
Haber was awarded the Nobel Prize in 1919 for the process he designed to generate ammonia from nitrogen gas in the air. With an industrial amount of ammonia, fertilizer supplies skyrocketed. As a result, food production also rose to meet the needs of a growing world population. This is a process that plants complete highly inefficiently using an enzyme called nitrogenase. Haber's goal was to set the specifications of his reaction as it relates to temperature and pressure. In addition, his work included optimizing his catalyst to encourage the reaction to proceed at an industrial scale.
Currently used metal catalysts are very similar to those originally specified by Haber. Such metals include ruthenium and iron. They require high temperatures to operate because the catalyst surface becomes blanketed in sticky intermediate compounds at ambient temperatures. At higher temperatures, the reaction becomes endergonic. An increase in pressure, as outlined by Haber, restores the downhill nature of the reaction. The specifications for the process were 650 to 750 Kelvin and 50 to 200 bar using metal catalyst.
An ideal catalyst would be the most perfect fit for the Haber-Bosch process at ambient conditions. Such conditions were specified by research to be 373 Kelvin and 1 bar. Because it occurs at ambient pressure, we can use simple chemical equilibrium thermodynamics to write a relationship between the equilibrium constant and the extent of a batch Haber-Bosch reaction.
To determine the equilibrium constant at 373 Kelvin, we must first calculate the Gibbs energy of reaction and enthalpy of reaction at 298 Kelvin. Using this data, we calculate the equilibrium constant at 298 Kelvin and then adjust for temperature effects.
Using a stoichiometric starting reactant basis, we can write each of the substance's mole fractions as a function of the extent of the reaction. By applying ideal gas behavior at 373 Kelvin and 1 bar, the equilibrium constant product simplifies to leave one equation in one variable, the extent of reaction. Solving numerically, we find that the Haber-Bosch process generates 1.596 moles of ammonia for every mole of nitrogen gas fed.
Thank you.
Thank you.